All right, let's talk about electricity. Ever wonder how it actually works? Well, we're about to break down one of the most fundamental ideas out there, the series circuit. And to make it super simple, we're going to use an analogy that, we can all get behind. A single lane highway. Yeah, trust me on this one. Stick around and you'll see exactly how a little bit of traffic can explain the flow of electricity. So, what even is a series circuit? Well, just imagine you're on the simplest road trip ever. The electricity? That's just our line of cars. And in a series circuit, all those cars are stuck on a highway with just one lane and absolutely no exits. None. Every single car has to follow the exact same path, one after the other. And that simple idea, that one path rule, that's the key to, well, everything else we're going to talk about.
Visit youtube.com/avidsystem and don't forget to subscribe.
Every highway has its rules of the road, and this electrical one is no different. So, let's start with rule number 1, which is all about the flow of traffic, or in the world of electronics, what we call current. And the rule itself? Incredibly simple. In a series circuit, the current is constant. It's the same absolutely everywhere. It really doesn't matter if you measure it at the beginning, slap bang in the middle, or right at the end of the circuit. That flow is always going to be identical. And this is where our highway analogy really makes things click. Just picture it. You're standing on the side of the road counting cars. Let's say 10 cars pass you in 1 minute. Well, your friend who's standing a mile down the road, they're going to count the exact same number, 10 cars. Why? Simple. There are no exits. The cars literally have nowhere else to go. That steady, unbroken line of traffic, that's exactly how current behaves in a series circuit. Of course, no highway is ever perfectly smooth, right? There are always going to be obstacles. Toll booths, speed bumps, maybe some traffic jams. In electronics, we call these obstacles resistance. And that brings us right to rule number 2. And this rule is just good old-fashioned addition. To figure out the total opposition to the current, you literally just add up the resistance of every single component in the chain. It really is as straightforward as 1 + 1 + 1. A road trip analogy just makes this so intuitive. I mean, if you hit 3 separate traffic jams on your way, your total delay isn't just the time you spent in the worst one, is it? No, it's the combined delay from all 3. Each and every obstacle adds to the total struggle of your journey. And it's the exact same in a circuit. Every single resistor adds its own little bit of resistance to the grand total. Okay, so we've got our traffic flow and we've got our roadblocks. But what's pushing the traffic along in the first place? Well, that brings us to our third and final rule. And this one is all about the power source itself, voltage. Now, here's the key thing to get. The energy from the power source, say a battery, it isn't just dumped on the circuit all at once. Instead, that energy gets shared out among all the components. Each part kind of uses up a piece of the total voltage. We call this a voltage drop. And listen, this isn't some weird side effect. It's a feature that engineers use all the time. It's a fundamental trick for taking one big power source and getting smaller, really specific voltages for all the different parts of a device. So let's jump back to our highway for a second. Think of voltage as the fuel in your car's tank. A tiny little toll booth, yeah, that barely uses any fuel to get past. But a massive hour-long traffic jam, that's going to burn a whole lot more. The total fuel you use on your entire trip is just the sum of the fuel you spent at each and every obstacle. And in a circuit, the battery's total voltage is the sum of all those individual voltage drops. Simple as that. And this visual just drives the point home perfectly. Let's imagine our batteries providing a grand total of 12 volts of power. As you can see, that whole 12-volt pie gets sliced up and divided among the 3 different resistors. The first one takes a little 2-volt slice, the next one takes 4 volts, and the last one takes a big 6-volt piece. And when you add them all up, 2 + 4 + 6, you get right back to the 12 volts we started with. Every single bit of power is perfectly accounted for. So we've got these 3 really clear rules, right? They make series circuits seem pretty simple, super predictable. But that single path design, the very thing that defines it, it creates one huge practical weakness. I call it the all or nothing problem. Okay, and this right here, this is the Achilles heel of the series circuit. It's so clear when you see it like this. On the left, everything's great. Current is flowing, all components are on. But look at the right. Just one little part has failed. And because there's only that one single path, that one failure is like a bridge suddenly collapsing on our highway. Boom, the entire road is blocked. All the traffic just grinds to a halt. You've probably seen this in real life. Think about those old school Christmas lights, right? One bulb burns out and the entire string goes dark. This is exactly why. So this all or nothing problem, it's a major drawback, which is why, we don't use series circuits for absolutely everything. And that leaves us with a final little question to chew on. If a single break in the chain shuts the whole thing down, then how come when one light bulb in your house burns out, all the other lights stay on? Well, that sounds like a puzzle for another time, and maybe, just maybe, for our next explainer.
Thanks for watching.